very impressive. So I talked about the standard deviation. So let us see what that is. So let me first of all find it by using that free calculator. So just type standard deviation, and here comes the calculator. So once I start typing it, that's something we can always utilize. Let me, for just in case, share the link to everyone. This calculator, I think it's great little tool. So now I will go to the exercise 9 and copy data from the first set. And once I copied it, then I'm gonna paste it in the calculator. So let me paste and make sure there are commas entered after each of this number. And once I enter all those little commas, then we will be able to find standard deviation, as well as the average, as well as mean for that sample. Please notice that we always treat this group of data as a sample. That's important. So not a population, but a sample here. So when I click on calculate, I will get a pair of numbers here. So one of them is a sample mean X bar, which is equal to 7.15. 7.15. To be honest, I don't think that population is really supposed to be there, because we always find standard deviation or mean or whatever else for samples of data. Because if you get a entire population, it's just way too big. That's why I don't think that's really relevant in most of the cases. That's why if you wonder when you use a actual population, the answer is never, because we always work with samples. But that's a great observation. So great idea that you asked that. So now what is that we found? The average mean for the sample should sit somewhere in the center. So 7.15 in this case seem to be the average of waiting times in some particular bank. So the average waiting time is 7.15 minutes. And the standard deviation is 0.47. So I will use this to give the ballpark. So this way people will know how much time they need to spend by staying in the line in that bank. And you may be a little bit luckier, so you have less time to spend, but maybe not. So it looks like if you add 0.47 to 715, that's going to be approximately about 7.6, let's say approximately like half or something. And if you subtract, it'll be something like 6.7, something like that. So in between of 6.7 to 7.6, so that gives you the estimate how much time you need to spend in a bank in a line. So from 6 to 7 or even 8 minutes waiting in line. So that's what we actually calculated in this particular exercise. And the key idea is, of course, to use the tool, to use the calculator, so the one that I utilize, that standard deviation calculator. And of course, we don't use a population but we use sample standard deviation. So it should be always for sample. Anyways, what else is here? Well, it turns out that there's a story in the textbook that is related to finding so-called median. So you can see that we looked at a few things in the section. So we found the standard deviation for the exercise. There is a word variance that happened to be a square of standard deviation. So I don't really think we need to worry about it because it's never been used anyways. Range, well, that's something that we already encountered before when we splitted our samples into classes. So we saw the smallest, the largest, so we saw how sample actually ranges from where to where. That's another familiar characteristic. But turns out that there's also so-called median or middle element that we can consider here. So let me say a few words about this. I just want to take a sample, but then I need to rearrange it. So looks like in this exercise, in this page, there are plenty of samples for us to consider. So I'm trying to find the most interesting sample. Well, you say, Alex, what is interesting for you? Well, like a jack in the box, for example. So I can try to see how this exercise 11 will look like if I try to do a little bit of a study of this particular bunch of numbers. So what I do is I will put these numbers that you can see here in exercise 11 in order. So I want to rearrange them. And I think it'd be a good idea for me to get a room for this. So I'm going to share the board, the clear board with you. So now I can try to get a sample elements rearranged from smallest to the largest. So I start with 74. That's the smallest here. Then we have 109 that appears twice here. We have one and the other 109. Then there's also 200 and 29 and then 255. So 229 and 255. So I just need to get a bunch of numbers. So I'm copying what they have here in the exercise so I can tell you one interesting and exciting story. Now it's 300. There is a 300 even, then 328 here. 328. There is also 377. 77. And no more 300, so we have 481 or 428. Okay. So it turns out that sample here that has a size 2, 4, 6, 8, 10, 11 elements is what I want to arrange from smallest to largest, because then I can find the median here or so-called middle element in a sample. So the middle element in the sample, well, should be like a half, right? Or 50% taken of my sample size, which is 11. So it's like 50% of sample elements. And when you do this multiplication, you get something like 5.5. Let's say what? There's a fifth place and there is a sixth place in this sample, but there is no element on the place 5.5. Well, it turns out we need to find the middle element of the sample by adding these positions together. So I add what sits on the fifth place, which is 255, and the next position, which is 270, and divide this sum by 2, and this will enable me to actually see what's supposed to be in the middle of the sample. So I say, Alex, actually, you should be a little bit more careful because there are 5 elements here and there are 5 elements here, right? So in the middle will be number 270, right? So I just wasn't careful. Notice that 270 is exactly the element that sits in the middle, right? And it does belong to the sample because there are 5 elements from it to the left and 5 elements from it to the right. So the middle element is 270. So how to find it? Well, I produce the decimal, so I need to move to the next place. So it turns out whenever we get a decimal like 5.5, then we just move to the next position and we get the element that sits on the next position. And I guess you can intuitively see that indeed 270 should be in the center of the sample because there are 5 elements to the left and 5 others to the right from it. So it's right in the center. So we find median, middle element. Well, analogously, I can find various other percentiles because median is really a half or 50% of my sample. So it turns out I can find the 25% of the sample analogously, and people call this as a first quarter or first quartile. So what I do is take 0.25, a quarter, and multiply by my sample size n, which is 11 in this case, right? And see what we're going to get. And of course, a good idea is to use a calculator for this. So if you multiply 0.25 by number 11, you're going to get something like 275. So when you get 275 here, again, this is going to be another decimal, right? And looks like we already have an idea what is done in the previous example. I move to the next place, so I get to position number 3. The third position here will have a so-called first quartile, first quarter of my sample elements. And of course, you can see that it looks nice and intuitive. So you have 2 elements here and 2 elements on the other side, right? So Q1 sits in the center in between of this first group of elements. Well, analogously, we can find the third quartile, or so-called 75% of the sample elements. So it'll be like 0.75, right? That we need to multiply by sample size, which is still 11. So when I do this multiplication by 11, I'm gonna get something like what? 8 and a quarter, something like that. So we get again decimal number, and once you have the decimal, you always move to the next position. So that's going to be 9, and then I take from 9th place. So it looks like it's somewhere here, right? Whatever sits in it. So please notice the idea of arranging the elements of my sample is very, very important, because if you did not arrange your sample elements, well, then anything could sit in that place, right? Because you can reshuffle those numbers any way you like, and then the whole process would not make much sense, because you can get just about any number on those places. So my third quartile is 377. And the first quartile is 109, 109. So it looks like I found 25%, 75%, as well as 50%. Median is like a second quartile. It's the same thing, but people usually like to call it as median. So this method enables us to find various percentiles. And you can find, for example, 10% of sample elements, or people call it as P10. So it's like 10% that I need to take off my sample size 11. So I could just try to find out what this is by using same exact process, just put 0.10 or 0.1 and multiply it by sample size to get 1.1. And this means that we have next place, which is the element that sits on the second position. And this is going to be one right here. So position number 2. It looks like we have a method to identify any of these so-called percentiles, 25%, 50, 75%, or just about any percentile that you can think of. One can say, well, Alex, what is this for? I mean, those percents, you're just playing with the sample elements, and how can we possibly utilize this? And turns out that the usage of this is tremendously important in order to see if all the elements of sample should really belong to it, which means that some of the sample elements may not be correctly placed in a sample. So for example, one can say, what about 74? What about this first element? Is this really good element? Because it looks like it's much smaller than all of the others. Maybe it should not be in a sample. Maybe It should be 174. Maybe somebody made a mistake when wrote down this number. How can we identify this? In other words, how can we see if we have any outliers? So are there any elements that do not belong to the sample? And I'm going to show you the procedure of producing so-called box plot. In fact, that's my favorite little picture. It's a picture of the box. I know pretty well how to make it. Based on the quartiles, such as first and the third, I can produce the picture of that box, and those actually correspond to numbers 109, right? That's my quartile number 1. And quartile 3 is 377. We just calculated those, right? So that here's the third quartile, here's our first quartile. So we calculated those quartiles. And then I'm going to produce the special process that will help me to identify if there are any so-called outliers. So what I just did, I put fences, the so-called inner fences. So those fences where my sample elements must be in between. So all sample elements must be within those two so-called inside or inner fences. And of course, since we have an inner fence, then we also have outer fence. So on the outside of it, we'll have outer fence. And once you get beyond this outer fences, well, you're gonna get the outliers. So it turns out beyond those outer fences, we have so-called extreme, right. So we have so-called extreme outliers. Extreme, they're beyond, they're too far away. And turns out in between of those fences, we have so-called mild outliers. So based on the picture of the box, I will be able to produce those fences. And then depending on sample elements, I'll be able to identify if we have any outliers here at all. And of course, characterize them as extreme or mild. So the key question is, how can I produce those fences? Well, to go for the fences, I need to find the gap in between quartiles, which is called interquartile range. Enter quartile range. We know how to find range. We subtract the smallest from the largest, right? So all I have to do is just get the largest, and actually this is my Q3, and subtract the smallest, which is Q1. So it looks like we have those two numbers already. They are 377, and I want to subtract from it 109. Right? And of course, you can use a calculator to subtract. I can just try to subtract it without it. So it'll be 268, looks like, right? Something like that. 268. 268. So it turns out that this interquartile range, we need to multiply by 1.5. And of course, that's always a good question. Why I have to multiply by 1.5 this interquartile range? Well, the answer to it is not given in this class. Actually, in this class, we use the results from so-called mathematical statistics sequence that includes 3 classes in it. So if someone be interested in taking it, you need to, well, take it in the universities, 4-year schools, because in our college we don't have such a course. But I guess it's not very hard to just take 1.5 and multiply by interquartile range. And that's what one just needs to remember, because yes, it's been proved, but we kind of take it all for granted, I guess, in this class, because all those statistical results are actually, well, making a good sense. And once I multiply, I get 402 for this product. So again, we'll see lots of results that we'll utilize here that I just can't really give an explanation because they use some calculus ideas in order to come up with various formulas in statistics. But the idea here is that once you found this number, which is 402, which is a interquartile range multiplied by 1.5, well, then you can produce those fences by moving away from your sides of the box to the right and to the left by this 402. So I guess that's a nice number and very useful, because now what I can do is just move from my third quartile from the right side of the box by 402. In other words, I'm just gonna add with 377, 402, and produce the fence, which is gonna be at 779. So at this position, I will have to put that inner fence. And then once again, I'll put 779 and go to the right by 402 once again. So this will give us something like 1181. So notice that once I calculated these two numbers, I can put my fences at those positions. And analogously, on the other direction, I'll have to move from my left side of the box, which is a first quartile. So I'm going to have to subtract that 402 from both of those numbers and see what we producing in here. So it looks like it'll be something like 93 and then 293 with a minus sign, right? So just try to subtract. And then if I subtract once again, because moving to the left means we subtract, right? Moving to the right, we add. So if I subtract another 402, it's going to look like 11, and that's a 6 11 with a negative sign. So I've got this fences constructed. And now I can take a look at my sample elements and see if they all in between of my fences. So if all of them actually belong to the sample, if there are any mistakes in data collection. So the first element I see is 74. So please notice it's pretty close. That element 74 is pretty close to 109. So it is not beyond the fence, because beyond the fence will be something negative, and we don't have such an element. Next is 109. So it's already within the box and so forth. So it looks like on the left side, we're absolutely fine. We don't have any of these so-called outliers. So I'll look at the other side, and on the other side, the largest element I have is 481. So please notice that 481 is also pretty well lying within the ballpark, within the area allowed. So people just put this little thing like that. And this element is also fine. So the previous, the one before, is 428, will be even closer to the box and so forth. So we just usually look at the largest and smallest elements. And once we have them all belonging to our range, which is within our fences, then you can declare that you have no outliers in the sample. And this is a serious result, because if you don't have any extra or extraneous elements in a sample, then, well, it means you didn't make any mistakes collecting this data. So all of the sample elements are fine. And now you can use this to find whatever you need to find. Let's say mean, standard deviation, and all other little answers to the questions. So no outliers in the sample, again, because it was fully lying within those fences. So you have no outliers. So we'll do this process once again next time, so you will get used to this a little bit more. I'll try to find a sample for you that will have some outliers, so you will actually see that this process does make sense. But today's goal is just to introduce you with this procedure, as well as to find various percentiles. So let me try to find another percentile for you, and maybe then you can try to find one of the percentiles. So what about if I try to find 20% of the sample elements, which is going to be dealing with multiplying by 0.2, right? To get 20%, I have to multiply 0.2 by my sample size, which is 11. So I got 2.2 here. And again, once we have the decimal, we'll always move to the next position. So it's going to be the third place, right? That's the position that I have to select my P20, and the entry is 109. When you say, Alex, this was exact same as when we produced the first quartile, it was also 109. How come? It's 25%, or is that 20%? It is also 25%, and it is also 24% and 23%. Turns out our sample size is small. It's just 11 elements. And this process makes sense for big samples. So when you have 100 elements or 1,000 elements in a sample, well, then, of course, you're not going to get the same number for 20 or 25%. So then everything be different. But with such a small sample size, of course, you're gonna get repeating results. So how about if you try for a little quiz to find 30%? What is 30th percentile? What number in the sample is P30? So you need to, well, just repeat the process I did here or there, and then see which element in my sample actually corresponding to this 30th percentile. And put your answer as usual in the Zoom chat so I can record that you were around today. Okay, so take your time, don't send this to the whole class, just send it only to my name, please. Okay. And after you submitted your answer in the Zoom, you're free to go and enjoy the rest of the day and have a great day, and we'll continue again on Thursday. So I'm going to stop to record this.